I'm Adam Leventhal,
I'm Ben Necker.
and very excited for dtrace.conf 2024 um, to uh, to kind of take the pass the baton from Brian's State of the Union. We wanted to talk about work we've done building a USDT provider for Rust. Now, in particular, because like we're going to see a bunch of work over the course of the day that builds on this, that uses it. So wanted to start out as the foundation. So talking about the past, present, future, but we realized that like actually the present is like much more urgent and exciting. So we're going to start with the present of dtrace and Rust. So fairly early on in Ben's tenure at Oxide, fairly early on in Oxide, full stop. You said it was February.
February 18th of
There
2021.
we go. So
It's the
pretty
first commit.
pretty early, we figured out like we're going to want these probes. We've seen the use of USDT probes in lots of different uses in dtrace. And I'm going to talk about this later, but USDT I think is arguably one of dtrace's most successful accidents, or at least accidents in terms of the breadth of its utility. And again, I'll talk about that later, and its origin in perhaps too much detail, but you can go for it. So we've used USDT early on in Sun, in C programs. We used it in Java. We started using it in JavaScript and other dynamic languages. And in all of these, we've seen this virtuous cycle play out where probes give us better debugging. And then that better debugging leads to more probes, and that leads to yet better debugging. So we knew we wanted to kick this off early on and make it possible to add these dtrace probes everywhere we could conceivably want a dtrace probe. And importantly, we want to make it easy. And when I say guilt-free, I mean, like, it's not going to create overhead. It's going to be a thing that we can add pretty much everywhere that we find some salient point of interest. So userland statically defined tracing is for identifying statically these interesting places to dynamically instrument.
So, I think I want to start by kind of talking a little bit of just about how you actually mechanically add these probes. And it's, as Adam said, we wanted to make it as easy as possible to do that. And very early on, so that as you build the code, you're kind of doing it, you're sort of building these things side by side. You're debugging it yourself, you're building it yourself, you're deciding what the interesting things are as the developer. So you can, decide which points to instrument, as you're building it. And then as you debug it, you can say, well, I should have had this probe here. I'm going to go do that. So it's really just 4 steps today. In Rust, right? You just cargo add the USDT crate. Then you define this module that we have here. It's decorated with this macro called USDT provider, which just basically says, make this available as a provider. And then there's a bunch of function definitions in that, which just look like normal Rust functions. They have empty bodies, but basically the signature of that describes what the name of the probe will be and then what the arguments are. We'll talk about this a lot, but you can put, we started with sort of the integral types, things like integers, and strings, but then we ended up adding a bunch of really, really useful support for basically any Rust type, which is, I think, extremely valuable. So you can have as many of these as you want. You can have as many providers as you want. And then you put them in your places of interest in the code by calling, in the third bullet point, this my provider :something. And you'll notice it's a macro. That's the first thing that's interesting. And the second thing is that there's a closure here. The double bar is a closure in Rust, and it returns the arguments that you're going to emit in the probe. We'll talk about why that's important later. And then you just call dtrace. So you can see here, we're just tracing this first argument. And I had a little dummy program that's just sitting and incrementing this counter in a loop. You can see this counter going up. So it's very, very easy to add these things. It's so easy, in fact, that we're going to do it live in a few minutes, and I'll show you guys how to actually do that. And it's really just a few lines. I did want to take a little bit of a sidebar into kind of how this actually works, because it's a pretty cool mechanism. And so Brian had mentioned at the beginning that there were people who were familiar with Rust, but not dtrace, and that includes me. So I knew Rust when I joined Oxide, but I had basically knew of dtrace, but that was about it. And this was a really cool project for me, kind of coming in initially, because I got to work really closely with Adam, who built the fucking thing, and then I can understand exactly how it works. And it's a very cool mechanism. So what I have here is that macro, I ran a program called cargo expand, which is a subcommand that takes things like macros and derives and all those sorts of things and blows them up into the code that actually then gets passed to the compiler for code generation. And you can see here that there's a few things. We call this lambda here, or a closure here, to get the arguments. So that's that thing I mentioned where you provide the macro with a closure. And then we are destructuring all those arguments. And then we call this little inline assembly, this ASM bang block. We call this inline assembly. And really the important part here is the not, and then the arguments, which is the second line. So you can see we're passing in one of these arguments in registers. The USDT probes have this fixed, set of registers that the arguments are supposed to be put in, and we have support today for up to 6 of them. But this NOP is the really interesting part the part that I found really interesting when I first learned how this works. So these points, as we mentioned, are static in the program text. There's this NOP, and then we can talk about this later, but we separately record where those NOPs are in the text. When you ask dtrace to enable the probes, when you do that dtrace -n, whatever the probe is, it finds this NOP looking up that saved location, and it rewrites it. It dynamically rewrites that in the program text from a NOP to a trap. And so that traps back into the kernel. Kernel knows where these arguments are, and then it will run your set of actions that you've described in the D language, given all of these arguments. And so you can do lots of really cool things, like make probes that are conditional, or you will run actions that are conditional on other probes, and all of this stuff is really the power of dtrace that we've all seen. But the cool part here is that we talked a lot about the zero disabled probe effect. It's just a NOP in this case, so it really is as close to zero as you can get. And we'll see on the next slide actually how these is-enabled probes make certain things even lower cost. So this is the same cargo expand output, but here it's for this specific part of the probe that is this is-enabled guard. So in the kernel, we don't have these kinds of things. These probes are sort of always enabled, but in USDT, early on, they put in this idea of guarding kind of complex work in creating probe arguments behind this is-enabled guard. So here what we're doing is we're emitting some inline assembly. We have this is-enabled flag. We're emitting some inline assembly, which by default is just clear racks, or set racks to 0. And now when you actually enable the probe, in addition to rewriting that NOP, what we saw on the last slide, dtrace comes in and rewrites this clear to be a move 1. So it's sort of setting this flag to true, and then the rest of your code runs, right? So that's where this if is enabled is not 0, do some other stuff. So this is part of the reason that we provide the probe arguments as a closure, because if it's not enabled, that closure will not run. And we wanted to make very, very clear that that's an important piece. So if you can't rely on side effects, you can't rely on sort of anything. All you really should be doing here is the work that's needed for the probe. And that's kind of it. You shouldn't be doing anything else.
But it's also the case that even if computing the arguments to the probe, like monstrously complicated or expensive, like that's fine too.
Yep.
Because that's only going to happen when this is enabled predicate evaluates to true.
That's right. And so it's not literally 0 cost, and that you kind of have to evaluate this instruction, this clear racks, but it's about as close as you can get in any real system. And so, yeah, you can compute much more complicated arguments, which in fact we do. We'll get into in a minute when we talk about passing arbitrary Rust types by serializing them into JSON. So we'll talk about that in a second. But this is one of the really important things, I think, that made us feel pretty good about adding support for things like any Rust type, because that complexity and that the cost of doing that serialization is all only under probes being enabled. Right.
That's right. We wanted it to be easy. We wanted it to be guilt free. And this is the way that we minimize the disabled probe effect, something Brian talked about in the State of the Union, that the disabled probe effect was much more important in dtrace than the enabled probe effect. Enabled probe effect can be, significant depending on what we're doing here in Rust, but disabled, it's the cost of like this clear instruction, compare instruction, and a branch. Like it's not 0, but I challenge you to measure it in almost any kind of meaningful code. Certainly when, Ben was adding some dtrace probes to look at transactions against our database. Like you're not going to be able to measure those 3 very trivial register-based instructions in the context of a database transaction.
Some questions in the chat.
Please.
So one, just create support workbench other than x86. Obviously, we're only using x86.
Yes. So
Yeah.
we support x86 and also ARM64 for Mac. So I'm going to run these on my Mac, which is one of their ARM-based Macs. So we support both of those.
Yeah, and the nice thing is like a NOP is a NOP in every assembly language. Now, clear, whatever. It's a nice instruction, but we have to specify the register. But a lot of it is very similar from architecture to architecture.
Then another question: does the first argument always have to be borrowable as a U32?
No. So we you can put any types you want that are supported. So we natively support all the integral types of any bit width, integer types of any bit width, and strings. We also support through JSON serialization, which we'll get into more in a bit, any Rust type that's annotated with this serialized derivation. So basically, if you can serialize the type to JSON, which you can do for almost any type, you can pass it. And then now it'll get passed over to dtrace as a string in JSON. But
You really are a big surprise. Like that's coming up.
Sorry.
Stay tuned, everyone.
Yeah.
Be patient.
We'll get that. You're right. So no, we do the borrow part is because we do a little bit of work to try to borrow things if we can. So the type has to be borrowable, but almost every type can be borrowed. So it's not a big deal. But we do that basically just to avoid copies wherever possible.
Right.
Yeah. So like I mentioned, we're going to do it live here. So I'm going to share something else. I'm going to share a terminal, and I want to show how we actually add these to a real program. So I'm in this little program that Adam wrote called System Simulator, which is a tool that we just use for kind of simulating a storage system where you have a client that's submitting requests to store data. The back end of that is sort of doing many requests and trying to handle many requests in parallel. The details of the system itself are not that important, other than to know that if you look in the source code, there are a few different parts, but we're going to look actually at this persist, which is representing kind of the actual persistence layer that's sort of doing the work of storing the data. So, so this is unmodified. I just cloned this. This is on our Oxide Computer GitHub repo. So you can clone this yourself.
This is further simulating. You listen to this talk and you think, hey, dtrace probes, I'd love to add them.
Yeah.
How would I do it?
Yeah. So I'm going to run this program, as is without any probes. And you'll see that what we're doing here, I should build it first. When Adam wrote this, originally it just has logging statements in it. So we're going to see what those do, and you could kind of see it like doing a bunch of work. The details here are not super relevant other than, there's a client that's like sending requests to do work. Those have some ID. There's a background task, which is processing those in parallel with some parallelism. So what we're going to do, like I said, we're going to go into this persistence layer here, and we can see the important part that I want to look at first is this enqueue function. So you can see, hey, we have a debug logging statement, which is starting the persistence. It says, cool, I've gotten this ID for my persistence request. I'm going to go do some stuff, pretend to do some work. And then later we will say we finished that work, right? We'll let the client know that we actually finished doing that persistence. So as I mentioned, the kind of first step here is cargo add USDT, which is very easy. So then if you look at the persistence code, we're going to add here, the first thing is the provider and the probe definition. So we can do USDT provider. Let's call it persist.
Yeah. So with the USDT create, you have to define your probes, your provider, your probes. And so what Ben's doing here is just, we've got this attribute macro. It's going to emit other macros, but this is the definition of each of the probes. Is a probe named enqueue and probe named persist, and each of them take a U64 as the only argument that you're going to pass to this thing.
Worth elaborating on the filth that we're crawling out of in terms of doing this in other systems. This is much more of a pain in the ass. Actually, if you're in a C-based system, it's actually a lot
get
more
to that and
simple.
talk about when we talk about how we built this originally. I think the first stop is going to be like how you would do this in C, which is actually how you used to do this in the USDT crate with like a separate .d file. We'll get there though.
Yep.
Cool. I don't know. I thought it was pretty neat. Okay.
Anyway,
No,
it's
we'll have a lively Q&A session at the end of it.
So this enqueue function, I'm basically going to, probe the entry effectively and the exit of this enqueue function, which is the work being done by this persistence layer. Where we have this logging statement, conveniently, we're going to say, hey, that's a logging statement. You might wonder, where do I put my probes? This is one of the good examples. Anywhere that you might log something is a potential place that you might want to put a probe, because obviously it's a place of interest in terms of monitoring the progress of the program. And so you might want to probe that, especially if it's something like, I'm about to start some expensive operation, or I've just done some, or something failed, some operation failed. Those are really good examples, because you may want to sort of know what happened during that. And so tracing the beginning and the end is a very common pattern to sort of conditionally do, other tracing sort of during that processing.
If you've ever like looked at a log statement and thought, oh, geez, I recorded this data, but I actually wanted some other data, or I wanted to know what was happening around the log, or I wanted to know what happened right after or right before. That is some of the utility of these statically defined probes in your Rust code.
Right. So I'm going to put a persist : enqueued thing, and I'm going to probe, and I'm going to return the ID there. And then I'm going to do persist : persisted. And again, returning the ID here like that. So if I've done this all correctly, we should just be able to cargo build this, and it'll now build all the USDT stuff. So it'll take a bit longer. There we go.
Nice.
Enqueued. Oh, right.
What do we call the thing?
I think I called it enqueue.
Yes, perfect.
Yeah, enqueue.
Nice.
Okay. The cargo build this. Now, if I do dtrace, what I'm doing here is I'm going to I'll get to this minus cap in a sec, but I'm basically just saying I want to trace that ID every time either the persist enqueue or the persisted probe fires. So I'm going to run this.
Persist is the name of the provider that's been created. We're saying let's turn on everything and then see the ID that we're printing.
So there you go. You can see that it's basically just incrementing this counter, persisting things. Here at this point, it's doing it in serial. If we caught the beginning of it, it would be doing some of them in parallel. But by this point, it's sort of backed up. The queue is full, and so it's sort of processing them one at a time. But you can sort of see how easy it is now to add these probes to basically any Rust program.
I mean, it took us longer to install Chrome.
It took me much longer to install Chrome than it did to do the work. Okay, so let me go back.
And you want to talk about cap Z. So, when and this can become more evident later on, but when you start your dtrace program, you specify like what you want to probe. Dtrace, the system will go out and look for these probes. Now, in the case of these Rust usually and statically defined tracing probes, they don't exist yet. Like they only exist once after the program starts running. So minus cap Z to dtrace says, and in fact, why don't you run it without minus cap Z? We should show, but minus cap Z to dtrace says, dtrace, don't worry about it. We already have them running somewhere. Okay.
Well, I think it worked because they're in. It's loading. I'm doing minus Z.
Oh,
minus
sorry.
Z, right?
So we actually, I'm actually a little surprised that worked. We'll go look at that later. But minus Z says dtrace, like, don't worry about it. If you don't find these probes, like, just keep on trying. And if they appear later, I know what, because we're on that. Oh, and we'll talk about it later. Anyway, little reveal here.
There you go.
So minus cap Z can be important. The reason minus that by dtrace by default will kick you out if it doesn't find any probes is if Ben had typed, had fat fingered the name of the provider, or we started to look for a system call that didn't exist or whatever. We dtrace think, that's probably a better user experience is going to be to tell the user, hey, there's no such probe. Is that really what you meant? And if what you really meant was this, then add minus cap Z.
Yeah.
And we'll explain why that worked and why we thought it might not in just a little bit.
So we did it live.
Sure did.
Yeah. So now Adam's going to talk about
I wanted to talk a little about the USDT origin story. And this is going way, way back. So before dtrace, Brian mentioned this in the State of the Union, there was other dynamic tracing facilities in the Solaris kernel that we were learning from. Dynamic in terms of how they worked, but not in terms of not systemic in scope. And in particular, there was this facility called Lockstat, and Lockstat was like fairly amazing. Lockstat would dynamically modify the code in locking primitives, obviously like a very performance sensitive, delicate piece of code, but dynamically modify the code in a running system in locking primitives to be able to gather statistics about kernel locking. What are locks that we're holding for a long time? What are locks that are heavily contended? It was an extremely, extremely useful facility. And as part of doing the dtrace work, one of the things that Brian did was to fold that lockstat uh, dynamic instrumentation methodology into a provider. So then lockstat just became one of the providers of dtrace, and the lockstat command became a dtrace consumer. So, and then we were able to use those lockstat probes in concert with any other dtrace probes to make even kind of more nuanced and complicated investigations of locking. So really cool. And we thought, hey, wouldn't this be nice in userland? We did all this userland tracing stuff with the PID provider. Wouldn't be nifty to be able to look at userland locking primitives. And so I started building this thing that we were calling plockstat or plockstat.
I guess you're not going to speak ill of the dead in terms of walking for tentacles.
Oh, I didn't know that he had.
Oh,
right.
You tried to do the slot wrong.
Oh,
He was extremely bad. He's an awful. I thought.
oh, no, I didn't know. So the late great Roger Faulkner apparently made a swing at this. I did not know that. I was just sort of sent in as a youngster to like not knowing that there were already corpses there.
Yes.
So
Like,
but I started like dropping these symbols around libc, and we took a look at it. We're just like, no, this is not it, and we can't integrate this. And so we integrated the bulk of dtrace, and we said, okay, let's pause. Let's think about what we want to do from plock. So we came up with a new idea, and the new idea was to do something a little like quite a bit more generic, rather than just me going in by hand and sprinkling these shibboleths of probes around the libc locking primitives. What we would do is modify these the locking primitives to identify the points of interest in the way that we just saw Ben doing for our example. And then we would stash the metadata associated with where the locations of these points of interest were in the binary itself. In previous attempts, it was this unholy knowledge between dtrace and a command and the implementation, but rather saying, let's remember where we put these probes by gluing it into the ELF file, into the command, or into the shared object. And then when the programs start, we use the metadata that tells us where these probes are to register probes with dtrace. So when a program starts, I also this description of these probes down into the kernel. And why we did this was to make small modifications to make files. Make files being how we used to make C programs back in the day. I don't know if I have to specify that. But we had to make, it's kind of a small change to the build process to generate this object file. Now, in thinking about this, I was reminded that I actually had preserved this document for how we came up with this from the archives. So I was digging through my files last night and unearthed this thing that I was fairly sure that I had. And I want to zoom in on part of it because it actually describes the mechanism like pretty accurately. So on the far left, you can see there's like this pile of files that represents our input C files. And the C files get compiled into object files, and then they get split. And we have our object files get further modified, where we kind of figure out where the probe points were. And then we create this new object file, which I was calling trace.o. And it to kind of keep that metadata. And then in that make file, it all would get glued together at the end. And this is more or less how USDT worked in C, worked in a lot of different systems for a very long time. Now, when I'm showing this to like patent lawyers at Sun way back when, now I think there is a patent on this, but it's all been, it's all based on the MPL. It's all like in the public. So, there's an explicit patent grant.
There is an explicit patent grant. I got other things for it. 17 years.
Oh, it's just like in the public domain. Okay.
Well,
Whatever. Gosh, sorry. Walt Disney really knew how to keep their copyright. So anyway, in the public domain, doesn't matter, whatever, that's fine. When I showed this to the patent lawyers, they did spot a problem. We'll see. I'll just give you a moment to see if anyone in chat can identify the problem.
That's already on it.
Okay, yeah. So it turns out the patent lawyers really did not like that I apparently was working on this while in China, because apparently if you build anything you build in China belongs to China, at least what they told me. I don't know if this is still the case. And they're like, it is very important that you did not finish thinking about this while in China. You might have started thinking about this in China. And also, please put away this document. We don't need to see it again.
Please destroy it, but I'm not asking you to destroy it.
That's right. Right. We've never seen it. You've never seen it. Let's move on. Okay. So moving right along from the archive. Okay. So USDT, I think it is fair to say, was kind of an accidental hit. Like we knew we wanted to build this Flockstat thing. We did Flockstat was great. I don't even know I've used Flockstat that much. Maybe you're like looking at me like you've used it a ton. I've used it some. Sure. Flockstat was great. And we knew we'd add probes to things like Postgres, like when are we starting a transaction, when are we completing a transaction. But then it found surprising life with tracing other languages, in particular dynamic languages. So things like JavaScript and Java and Ruby and PHP. PHP.
No, Liza's suggesting that the P in Blockstat stands for $2 Shanghai.
Yeah, that's the homage to the Pudong hotel back there. That's lovely. So we again, we didn't see this coming for USDT. We didn't see the utility, the breadth of the utility, but I think that is arguably the place where we've seen some of the most development and use of dtrace in like the past 10 years or so.
We did have SDT at the kernel, which is also
Did have SDT in the kernel. We used SDT in the kernel a ton for the dynamically defined tracing provider for the kernel to look at, like disk IO, process lifecycle stuff for sure. But I think that the surprise of USDT was its applicability in like dynamic language and in tracing places that we didn't sort of know how we were going to trace, right? Like in Java in particular, when you're in this JIT, like how do you know, like the functions don't exist to instrument? How do we even talk about it? So we found some amazing utility there. And at least it is enabled. We've already demoed is enabled, but I want to talk about where that came from. So early on in C with USDT, I guess we sort of convinced ourselves like things are sitting around in registers anyway, so maybe it's not that expensive to just like pass to the probe. Like it's again moving some registers around. Like we're on Spark, we're not moving that fast anyway, so who's going to notice? But then when it came to dynamic languages, we discovered that some of the most important arguments that we were passing from these probes were very expensive to compute. Like as I recall, in Java, even like discovering kind of the name of the method, the name of the class, these things were not right at hand. It wasn't a couple of pointer chases away, but it took a lot of work to figure out where we were.
Ruby in particular, that was Ruby was devastating.
Yeah,
to get this information.
Yeah, because I think we did.
I remember like what was the actual use case where like we had got to do something else.
We did this while you were joined and I was at Delphix, and we cooked up this stuff.
Is it able?
Yeah. No. Was it before that?
Yes.
Oh, really?
Yeah, I'm telling you where I was.
Oh, really?
When you and I were talking on the phone.
Okay.
And you were describing this, and it was
Okay.
like, yeah, that's very,
All right,
very,
there you
very
go.
good idea. No, it's that Sun. It is. No, it's going to be prior. It's like 2005, 2006.
Oh, wow. Okay. Much earlier than that.
Yeah,
All right.
I think it is the Ruby. I think we done the Ruby provider. I had done the Ruby provider though before I worked there.
Okay. There we
So
go.
that made me where you're getting the joint tie-in. Scott Barron at joint done the provider. It was devastatingly slow.
Yeah.
Anyway,
There we go. You're right. So devastating. So with regard to disabled probe effect, and we really wanted to remove that disabled probe effect. So as Ben was describing earlier, in C, we would generate a macro. I almost hesitate to call it a macro just because I'm so in love with Rust macros and they're so beautiful, but like these like search and replace text strings feel like so primitive, but it was a macro that would evaluate to 0 with disabled. And then the dtrace kernel would overwrite the instruction to drop in a 1 rather than a 0. And then we can add this simple guard around whatever was expensive.
So I think our first version of the USDT Rust crate really took basically everything that was just described in terms of how you glue these different parts of the object files together to produce this final binary, all of these macros. And we really just like made the Rust compiler do that for us, but it was very much like a transliteration of the C process. So we at Oxide, we use Illumos for our host operating system. And so we were focused on Illumos as the first consumer, and we really modeled it after that process in C. So the idea for the first implementation here was to force people to write the provider definition the way you would in C, which is in this extra file written in the D language, where you describe the provider. Effectively, that module that we saw 10 minutes ago, you would write a very similar thing in C, or in this D language, excuse me. And then you would have a few extra compilation steps where you would take that, we would process it, we would generate some sort of extra metadata in these object file sections and glue those all together. So this is very natural in a makefile centric world where you already have make is basically just an automation around a bunch of shell commands. There's one way you could think about it, right? And it's not uncommon to add these extra steps, and they all get sort of wrapped up into the final targets anyway. So you don't really see them too much. It's not that big a deal. But in Rust, this is pretty burdensome. The more you add these kind of build steps, if Rust has the notion of a build script, something you can run at before compile time of the main code, but they are a bit unusual still. They're not widely used. And they're, adding more of these steps is definitely like a burden for most Rust developers. And those were definitely, I think, unexpected. The other big thing is that Rust has this idea of there being no life before main runs. And what this really means is that they make very few guarantees. The Rust language makes very few guarantees about what code you can expect to run and to be available before the main program runs. So as an example, if we're writing this probe definition in D, we want to take all of this and generate at the end of the day something called doth, which is the dtrace object format. These sort of extra metadata sections are written in this kind of mini ELF-like format, and we want to send that down to the kernel through the octal that Adam mentioned. But to do all of that, you have to do a bunch of processing of these of the provider definitions, of the probe definitions, to generate this doth. And it's a pretty tricky thing to do before main, right? Because you don't really have access to things like collections, like a vector or a B-tree map or anything like that. And, you can't really build these complicated string tables that are inside the doth format. So it's pretty hard to do all of that before main runs in Rust, at least reliably. So we decided to sort of take a step back and instead, we store that probe metadata in a different kind of, not in doth, but in a different kind of stripped down metadata format in these probe records, we call them, store this metadata that you need to construct the doth. But then we require this explicit registration step, which is a bit of a wart that we'll talk a little bit about later. At the same time, it's kind of nice. Rust is I think, has an emphasis on things being pretty explicit. And I think that's a good thing in general. So it's not, I think, too onerous to have this registration step. And what that does is takes that metadata in this very stripped down format, constructs that doth, and then does the ioctl that we described. So this is sort of where we started. And again, this is all kind of in the Illumos only world. We were just on x86 at this point, really kind of focused on getting something that would work, getting that the metadata described and sort of understand what we need to actually do to register these probes at runtime. And then enter macOS.
Yeah. So, yes, this is a typographical joke, and yes, that is a form of dad joke, but macOS works different. So one of the ways in which macOS works different is, at first we built this mechanism in Illumos, we tried it in macOS, and we got very strange results. It just turns out like the implementation is a little different. They use some of the fields differently. Some of the addresses are different. It's different. But one of the ways in which macOS is different in a terrific way, it speaks to some of the strength of Apple. So Apple ported dtrace to macOS 10 in 2006. I should note also, it was like a surprise to us. And it was a surprise to us in the dumbest way possible. The folks at Apple wanted to meet with us. They were evaluating dtrace. They said, evaluating, that sounds great. We'd love it if we ported it.
They wanted us to come to Cupertino.
They wanted us to come to Cupertino. I didn't remember that. But
They asked us to come to Cupertino. We're like, no way. If you want to meet with us, you're going to come to San Francisco. Like, that's going to be it.
And they did. They came to San Francisco. And like, that was also, I was not tipped off. And they came not with like, so tell us about dtrace. Like, what does it do? But it was more like in this structure, on this field, on the fifth bit, what is the significance of this? And things that the three of us, Brian, myself, and Mike Shapiro, the third dtrace author, looked at each other. Like, if any of us know, it's going to be one of us. No, three of us, no two of us, even though the answer to the questions.
I just in depositions that were less point.
So very, very specific questions. And we walked to that meeting, and the dummies that we were, we thought, wow, they had done their homework. Those were great, thoughtful questions. Of course, they were 99.8% of the way done with the report, which they then announced like a month later.
So nobody asked me a P-lock, proc-lock ordering issue. This one where it's like, you're very glad that you have, there's only one human being on the edge.
Yeah, exactly. So like the ordering of locks being a question, you're really only asking when you've got a bug. Okay. So, so they made this port. It was terrific, somehow surprising, but it was great to see. I think this is not fair to say, but one of Apple's greatest superpowers, among them are user experience and integration. And I think it's also fair to say that coming from Sun, these were not our superpowers. And one of the things that we're really impressed by with Apple's dtrace port was the UX and integration. So out of the chute, there were tons of processes, tons of USDT providers available just by default. In fact, if you're on a Mac right now and you would do a dtrace SL, you will see thousands and thousands of USDT probes in all of their core services, and they are still there, and they are still used, and they are still firing these probes. Very impressive. I think at Sun, we had a few probes like from the kernel group itself, like plocks that, but beyond like the kernel group itself, we did not have it. Like Apple's version of Perl shipped with dtrace probes. Sun's version of Perl did not ship with dtrace probes. So really great on the integration. The other thing that Apple did, which was amazing, was build that integration with the compiler and linker. So rather than having this, the Pudong Shanghai mechanism of doing a ex post facto modification of the object files, emitting a new object file, modifying your make file to link it all together, Apple instead just says, why don't we just make the linker able to do this whole thing, which is great. And what it meant is you didn't have to change your build process, you didn't have to change your make file. We were just, you just add the probes, and they're good to go. They're there in the Mako file, that their compiler and the linker emits.
So we took this idea and sort of ran with it a little bit when we built USDT to work on macOS. So we realized that we could get away on macOS with no probe metadata. There's no probe registration. There's still a function for probe registration, but it just succeeds all the time because nothing is required at all. Instead, as Adam said, the compiler and the dynamic linker are sort of working together to just like do all of this stuff for you. So instead of on an x86, like a Lumos machine, instead of emitting like this inline assembly with the clear racks and all this other extra stuff, we take those same macros and we emit totally different code, which I've copied here. So instead, we are emitting the same functions with the same sort of magical symbols that the C toolchain on macOS will emit for you. So that's what this like massive dtrace provider with all these $signs in here. The compiler is taking this probe definition and emitting a function that is called this thing, which has, this special naming based on the symbols and then also the arguments. And in Rust, we can do this instead. So that's not a valid Rust symbol name. So you can't name a function literally that, or at least you couldn't. I think you can today actually, but you couldn't do that when we first built this. So we use this attribute, this linked name attribute. Rust has a lot of code generation mechanisms for modifying how the actual code gets emitted, where things get linked, all that stuff. And so we could say, hey, actually, I'm going to call this function underscore something, but then you're going to call it, when it emits a symbol name for it in the actual binary, you're going to call it this, 397 character thing. And I promise that, you when I write this, you'll just transliterate it for me in the final binary. And then at the end, the rest of it is sort of automatic. So now I have at the bottom here, this assembly that we emit for the actual probe site. So instead of like a NOP and this clear racks or any of that sort of stuff, instead what you see here, so this is on ARM. So the BL is a call, and it's saying, actually, I just want you to call this function, this symbol called something, underscore something, which is that giant dtrace underscore probe, et cetera, function. But otherwise, it works very similarly. We're creating the arguments in the same way. We're calling your closure. We are unpacking them, putting them into the right register. So again, the register names here are platform specific. So it's X1 rather than, RDX or whatever it is on the other ones. But all of this kind of happens automatically when you run, when you emit these, when you compile your program. We're actually calling out to the C compiler to learn what these functions are supposed to be named. These symbols are supposed to be named.
To the D compiler.
Sorry. Dtrace. So Apple has a dtrace invocation that will generate a header file basically from these D definitions. If we do that to learn what these symbols are supposed to be named, and then insert them in the code that we generate from the macro.
Yeah. And so the result is like, we're kind of plugging into that Apple integration toolchain for the Rust USDT implementation on macOS.
And even though the actual kind of guts of this are pretty weird and janky, I think this was a kind of an important moment for us that we realized that the value of that integration in terms of like a developer experience where you don't have to, even the assembly that you're emitting is much simpler. You don't have to sort of the register probes thing. If we were only on macOS, there would be no register probes function. It would just do it automatically, right? At the time that the dynamic linker loads the program. I think that there's a lot of stuff that Adam's going to talk about later that I think we can take from this and learn from this, and helps us understand what a better future might actually look like. So the last thing I want to talk about in terms of building the process of building the USDT crate is the idea of complex types. So we hinted at this at the beginning, but
well, if just to talk about the origin, like, so we were using the USDT crate, and our colleagues were like, "This is great. Like, I love 16-bit integers, 32-bit integers, strings are pretty nifty." Our colleagues were very impressed. They also thought like, "Hey, what about like everything else? Like, what about all these types that I use to record stuff?"
Yeah,
and like having to unmarshal those into a pile of strings or like U64s or whatever seemed like kind of a pain in the neck. So we thought, like, how do we show off the rest of these the type richness of Rust and have that come through in our dtrace probes?
Yeah. So as Adam is getting at, Rust really encourages lots and lots of types. It's very cheap to make new abstractions and to put types together. But then, of course, we have to like unpack them all by hand if you wanted to use the original implementation of the USDT crate, which sucks. So instead, Adam had this really great idea of there's this very popular crate. It's one of the foundational crates in the Rust ecosystem, which is called SERDI, which is for serialization and deserialization. And it's extremely widely used, and we can serialize basically almost any type into JSON. And I think in like 2011 or so, the JSON action somewhere around there.
2014 or something like that. Yeah.
There's an action in JSON.
This was now a joint for real.
Yeah. That was for real.
Yeah.
So there is an action added in dtrace called JSON, which does exactly what it says on the tin, which is it would take a string that was supposed to be JSON, and you could inspect it in various ways. You could pull out keys or values and sort of understand, process the structure of JSON itself. And so this allowed us, I think, well, actually, before I do that, let me just sort of show how this works. So in Rust, you might name a struct like this, and you've got, say, two U32s in that struct. And you could just add this derive serialize on top of it here. And then you can just put that as a probe argument in your provider. You don't need to do anything. You don't need to destructure it yourself or do anything manually. You can just provide it as an argument. And what we will do in the probe macro that gets emitted, we will do this, which is we basically call that closure. We get your argument. In this case, this details type. We take that and then we actually call this toJSON function, which is really a wrapper around a SERDI function or a SERDI JSON function that takes your type and turns it into a JSON string. There's a bit of a wrinkle here, which is that the serialization is fallible. It can fail. And so we have to kind of wrap everything in this kind of result type. So you have at the top of it, you have like an OK or an error uh, um, key, which tells you basically, yes, the serialization worked and here's what it is, or no, it failed and here's what happened. Um, but other than that, we can now pass this JSON encoded object as a string. So just the char star to D, which has now this action, this JSON action for inspecting it. So you can pull out the OK or the error variance and sort of see what happened there. And then just sort of use this much more natural way of expressing uh, the object that you want to pass from Rust, which has these very complicated types, or can have these very complicated types, into the much simpler types that D has by default.
Yeah, and just to pick up on some of the themes that Brian mentioned with State of the Union, I think this really emphasizes the utility that goes into the development of some of these dtrace facilities. Like, is this the most elegant thing in the world? Like serializing things as JSON, shoving in the big kernel, copying in a string, and parsing through it? No, it's not the most elegant thing in the world. But it also was not that hard to do and gave us just a tremendous amount of utility and value. Like, it's unbelievable how useful this mechanism turned out to be, how little work it turned out to be. And like, yeah, is it a little icky? Yeah, it's weird. I don't know. But the like sort of real robust thing would have been just an epic journey that we weren't going to go on. And this got us probably 90% of the value.
I would also say that this is also like, it's kind of like it's a lot of work to do this, but it's work that's only being done
That's right.
when you have enabled the probe.
That's right. So when we talk about like disabled probe effect, if we weren't guarding this with an is enabled thing, it's like, yeah, it turned out you just added JSON serialization into my hotnet. Like, actually, that does make my transaction look very snappy by comparison. But yeah, we're only doing this when this is enabled. The other just quick point I'd make is that Apple did their dtrace port in whatever it was 2006. I said, Josh Clulo, our colleague here, had developed the JSON action in 2011. Apple has taken that in their port. Like, I don't know what cadence with which they're picking up stuff, but it's available in the Apple dtrace port. So this is not like an Olumos only spec.
Source code of which is presumably made available somewhere.
It's
part of the
license
license.
available.
Exactly. We've looked at it to figure when we were trying to figure out the initial implementation on macOS. We were trying to figure out they have slightly different struct definitions for their DOF stuff, and we're trying to figure out why.
Apple does seem to abide by the license and make source available. Is it the most convenient?
Is it the most abiding by the license?
Probably not, but I'm sure their lawyers will tell us it's just fine.
And one of the nice things, the last bullet point I want to mention here, this JSONification is actually what really prompted us to take the provider definitions out of D and put them in Rust directly. And I think that was it sounds like a small thing, but I think it's a big deal to not have this extra file lying around that you have to keep in sync and make sure is, up to date. And, then maybe you don't get the same level of type checking. And I think that was also putting them in Rust, I think added a bunch of, it made it much more natural, made it easier for people to do. They didn't have to like learn a new syntax really, because like these are just function definitions that look very similar otherwise to a Rust programmer. And I think that, is also going to show up in some of the themes that Adam's going to talk about at the very end about like how we could do this a little bit better.
But we needed to do this because we wanted to have one specified type. It wasn't an int, it wasn't a string. So we needed some way of specifying a type. And of course, we wanted that type validated. Like we don't want you to be able to call this probe with whatever. You want to make sure we know that you're giving it the right entity. All right. So now buckle up. We're going to talk very briefly about the future. Because I think that, we have this sort of accidental success with USDT. And it's been great for us here at Oxide, great in Rust. But it has made us think like, what would better look like? Now this title, the Oasis is happening. So back when we were at Fishworks, back at Sun, a colleague was doing some work to develop dtrace, and he came to us, to me and to Brian and to Mike, and started explaining all the ways in which dtrace was deficient, things he couldn't do, this and that. And we all kind of sat back And we had thought dtrace was pretty great, actually. And it let us do things. And I think my response at the time was, John, we like to think of our oasis as half full. So in this case, this oasis, this kind of water hole in the desert, it's great. Like and to quibble, feels dismissive, but I think it has made us realize like the ways in which this can grow. So we've used these USDT probes to we've got a ton of value. But like this macro that has mod functions, like I know it's sort of more familiar and it's like emitting more macros, feels like a little weird. Also, um, we have these, I mean, we mentioned this, but we take these records that describe the probes, we put them in an ELF section, which is really just something Ben and I made up. And then we have to massage those to turn this into the doc that we send into the kernel. See it on macOS with their linker involvement. We don't need to do it that way. But on Illumos and other platforms where you don't have that linker integration, you do. And the structure of these is kind of weird. Consumers also have to remember to call this USDT register probes thing. And that's sort of fine if you're sticking them into a binary. It gets weird if you have it in a crate. So for example, we have our web server framework Dropshot that Dave Pacheco and I worked on. It has dtrace probes. And we have to find a way to call register probes, and we do it when you're starting a server. It's fine, but it's also a little weird. And you have to remember to kind of sneak in this call somewhere. And even with the bulk of work under is enabled, it does feel like there's an opportunity to have even less disabled probe effect. And I just observed that like every tracer and compiler in different languages are all kind of doing their own thing. This thing did make me think like, okay, what if we had some standard for statically defined, dynamically enabled probe points for all the tracers? What if all of the tracers in the world, us and eBPF and anyone doing anything tracing got together, and this is just like not going to happen. I don't know why. It just seems so ridiculous. Like we're never going to decide like, oh, let's find common ground. Let's make a standard. Like standard bodies like sometimes work, but it does not feel a place where standardization. So, okay. Second big idea. I think Rust should natively expose dtrace userland probes. And this was an idea that was not originally by me, but Great of War, original author of Rust, wrote this issue in the Rust RFCs back in 2013. I think Rust should expose dtrace userland probes. Hey, me too. We all do. That'd be great. And so it was very encouraging when I stumbled over this to think like, okay, they were thinking about dtrace probes natively in Rust very early. So why would we do that? And what would that look like? So if we had first class probe definitions, we could avoid some of this sort of stranger macros generating macro stuff. The type checking that we do is okay, but relies on other kinds of type generation. We could avoid the need for explicit registration, which again is too easy to forget. And then I think another neat opportunity is to lay code. We could potentially lay code out in a more kind of a more optimized way. We could take all of this disabled by default code, all of our serialization of types, stuff that somewhere else out of the hot path, not just like under, outside of a branch, but kind of out of the flow of control completely, and do it more intelligently out there. So the thing I can imagine happening here is that Rust leadership on USDT and dtrace integration could lead to more followers. So one of the neat things that we saw is that other tracing frameworks followed this USDT mechanism that we built. And in some cases, like with SystemTap, even the command to generate header files, to modify object files was named dtrace. Like that these other tracers shipped with a binary whose name was dtrace. And why did they do that? Well, project had used dtrace to add probes to the program, and it was easier to follow and have those make files be backward compatible. So kind of weird, but I think that Rust, first class Rust compiler collaboration with dtrace could really lead to other tracers and other compilers and other languages following suit and kind of having that ersatz, that de facto standardization, especially as we see the benefit of even closer integration, more natural, more fluid, available by default, and with kind of like a simpler mechanism for registration. So, that is what we came with. I hope that folks now take the USDT crate and add probes to what they're doing, whether it's on macOS or on Lumos or other systems that support dtrace and support USDT. And I'm hopeful for the future of what USDT and Rust might look like.